All right, so let's take that last question and scale it up quite a bit and look at the gravitational force between the Earth and the Moon. And so essentially, it's kind of doing the same thing, isn't it? Right? The Moon, if something wasn't pulling on it, would just escape out into the universe, just leave. And so we have this force between the Earth and the Moon that's pulling the Moon around in a circle, and essentially that's uh, what we're measuring here. You may or may not know, but the moon doesn't go in a perfectly circular path. So we have perigee and apogee, which basically means it points where it's at different distances from the Earth. And we got sort of an average number, but I use it to my advantage to make this part random. So we have a formula. At first glance, doesn't look too bad, but the gravitational force, so when it's this special type of gravity between like planets and things in space, a lot of times it's a capital G, and that's because there's a constant involved that's capital G. So this gravitational constant, this number is on your formula sheet, or you can look it up, find it in the book relatively easily. This gets multiplied by the mass of the large object, which is obviously the Earth, and the mass of the small object, which in this case is hopefully, obviously, the moon. And then you're going to divide by the separation distance squared. So, all right, now maybe it looks a little bit messy. One of the big things also is you're going to have to use scientific notation in your calculator. And a lot of students either have never done that before or don't do it often and don't remember how. Um, but that's a big hurdle because if you're not used to typing it in a certain way, or if you're using a calculator that requires a different input method, then you may struggle a bit. All right, so let's look at this information. Some of these things are provided on your formula sheet. In fact, most of them are. The only thing that should be changing here is just this distance. Now, I don't like that it's in kilometers, so think kilo or K means thousand, and we can just sort of change this in line. So, another thousand, another three zeros of meters once we have that conversion done. Okay, so there's your R. We've got the M's, the G, everything else is a constant, so we can take and just plug in. All right, so the gravitational force is equal to the gravitational constant, which is 6.67 times 10 to the negative 11. And the units are horrible. I'll be honest with you, I never remember these units, and I always have to look them up. If I try to figure out what's going to cancel and survive, I can work it out, but I always have to stop and think about it or cheat and look it up. All right, but here it's newtons multiplied by meters squared over kilograms squared. And this was one of the things that I had in mind in the previous problem set when I said how the constants are designed to cancel things. So notice we're trying to get newtons as an answer, and we've got newtons right here. So we just hope that everything else just basically annihilates. So let's see if we can make that happen. All right, mass of the Earth, not something I expect you to know, but you can find it on your formula sheet, also in the book. Oddly enough, if you look around in the book, you will find slightly different answers in different sections of the book. So I don't know how or why that happened. It would seem like a bad idea for the mass of the Earth to change, but whatever. Then mass of the moon, same thing. You find slightly different estimates, I guess, for what the mass would be, depending on where you look it up. So please use this number or find it on your formula sheet. Then finally, all of this goes over that separation distance, so 383 million instead of 1,000, right? Because we converted away from kilometers to meters. We don't want kilometers plugged in. And then by the definition, that gets squared. So, yeah, that escalated quickly. If we check out the units, we can see that the meters squared here will cancel with the meters that get squared on the bottom. And then the kilograms squared cancel with the kilograms and the kilograms there. So thankfully the units are preserved and we can see where they come from. It's just a matter of plugging all that stuff in on the calculator. That's the part that's going to be a little bit tricky. Some of your calculators have a button that looks like it has two capital E's on it. It is specifically capital and specifically two of them. So if you see a lowercase e, that is not the same, or usually not the same. Um, you might have a button that looks like it says x10 to the x. You might have a button that's x10 to the y, which is, not a lot different, probably easy to find. Or you might have a button that says exp for exponential. You'll just have to look and see. If you can't find it, send me an email, check on YouTube, read the manual that comes with your calculator, whatever. But that's something you're going to need to get a handle on, because we're going to have scientific notation in several different points. All right. The first part's usually not too bad when we start multiplying things together across the top. And, instead of squaring, if you want to, you can multiply on the bottom. That's not too bad. It's usually the next step where students have issues with the calculator. All right, so here on the top, if you've figured all your buttons out, you should get 2.931661 apparently times 10 to the 37, which is an unbelievably just huge, massive number. And then on the bottom, when we take and square that thing, we have 1.4668. I think that's a 9. Sometimes I can't read my own handwriting. Times 10 to the 17. Right, newtons were the only units left over from earlier, so that's going to have to be the units on the answer. And then here's the tricky part. When you go to divide these, depending on your calculator, a lot of times you have to have additional parentheses around that denominator. So when you divide that second part, sometimes what it'll do is it'll give you the correct number in front, but it'll give you the wrong exponent. And it's because it did things a little bit out of order compared to what you probably had in mind. So again, the calculator can be a little bit of a hassle there. But if you get everything working right, you should get just about 1.999 times 10 to the 20, which is an absolutely massive force. But to me, makes sense because it's the Earth pulling on the moon. So kind of seems like it would have to be a big force.